two-step approach to learning. Step 1. Ensure, establish, and maintain the fact that Eout is approximately equal to Ein. So, two-step approach to learning. So, fundamentally, the learning produces G. Okay, so ensure that Eout of G is approximately equal to Ein of G. Okay. That's basically what this theorem is saying. Okay. But now we need to add another step, because we need to complete the loop, and we need to argue that we have learned, i.e. G is good, i.e. Eout of G is approximately equal to 0. So step 2 of learning is that, arrange or, get Ein of G approximately equal to 0. Okay. And if I accomplish these two, then together, since Ein is close to 0 and Eout is approximately Ein, which is close to 0, these together imply that Eout of G is approximately equal to 0. Voila! Okay. I have gotten to where I want to be for learning. Okay. And you might say, well, you know what? Why didn't you just go for this from the very beginning? Okay, I didn't go for this from the very beginning for a very simple reason. Okay, F is unknown. I don't know F. So I'll never really know Eout. I'll never know Eout. There's no way for me to, for example, compute Eout from the data. Eout is patently an out of sample and outside the data quantity. Okay. So I can never directly analyze this guy. But what's the miracle? The miracle is that I can develop a mathematical theory, okay? I can develop a mathematical theory in which I can analyze and say something about this guy. Okay, I can say something that En is close to Eout. Okay, that I can develop, and boom, here is the theorem. Okay, it's a theorem. You can take it to the bank. Okay, and, I cannot measure Eout, okay, by looking at the data. I cannot measure. Okay? I'll never know Eout, but I do have this link. I have a link that says it cannot be too large, providing that I also get En close to 0. So I'll never be able to measure Eout, and that's why this link has to be established theoretically. I have to just know that it is true. Okay, I'll never know for sure. High probability. So I will know with high probability that this link has been established. So I have to establish this link theoretically. Must be established theoretically. Now, it turns out that, later on we'll discuss a type of learning called nearest neighbor learning, where indeed you can go and analyze this guy directly, but generally you cannot. You cannot make any claims about this guy. And so we have to make this sort of indirect approach to learning where we get a hold of this guy and tie it to that guy theoretically. Okay. And then this guy we can measure. So we will know what this guy is. So this guy can be measured. Because it's in sample. It's in sample. We can just look at G and see how well did you do in sample. Okay. And in this two-step process is embedded this trade-off. So if you want to get in sample error small, you would like to choose the hypothesis set to be as large as possible. So here we want the hypothesis set to go up, large. Okay. But the larger you make the hypothesis set, you lose control of this, okay, this first step in learning. And so to ensure the first step in learning, you want the hypothesis set to be small. So you want the hypothesis set to be small in order to accomplish that. In order to accomplish this, you want the hypothesis set to be large. And so, they're trading off against each other. Okay. And then the machine learning expert comes. And first of all, you understand this trade-off, and you understand that there's this two-step process to machine learning. And you understand that you cannot just go, so the amateur, who I will never hire, just says, oh, let me take this nice complicated neural network and fit the data, boom! They are just doing the second step in learning, in good learning. Okay? But you guys, the experts, know that there are 2 steps in order to get good learning, in order to actually learn. And in implementing this 2 steps, that's where you're going to earn your money. Okay. So, in this class, there are very few lectures where I will turn around to you and say, you know what? I've earned all the tuition you're paying me. This is one of those lectures. I've earned all the tuition you're paying me. Okay. And why is that? Because this is what makes you an expert. The fact that you understand this trade-off, that you understand there are 2 steps to this learning process, and it's very easy to get this down. It's very easy to get E in down to 0 and forget about that. And that's a disaster. Okay. Because you haven't accomplished E out. The only way to accomplish E out is if you get this and that. Okay. Okay, so let me summarize now. We're at least with respect to finite hypothesis sets, we are now in a position where we can summarize our answer to the question, is learning feasible? Okay, so let me summarize it over here. And then we'll come back and bring the whole, and answer some questions that may be nagging you and bring this whole framework closer to reality, closer to practice. Okay. So, summary. Is learning feasible? Okay. Finite hypothesis set. Finite H. And I'm willing to spend some time here because the infinite H will not be so much different. So, okay. So the answer is yes. Okay. But there are some conditions. Okay. And the first condition is that you have to give up for sure. Okay. So, yes. Okay. And here is what we get. Okay. 1. Real learning is feasible providing we accept it as a 2-step process. It's a 2-step process. Okay, so 1. The first step, you get E out of G approximately equal to E in of G. And this has to be done theoretically. Okay. And it is coming with some conditions, but the most important condition is that we will never be sure of this. It always is with high probability. Okay. With high probability. Okay. And, so in order to accomplish the first step in machine learning, and there'll be some other conditions, okay, which I will mention, but in order to accomplish the first step, we have to do it theoretically, and we'll never do it for sure. We can only do it with high probability up to this error bar. Okay. And then the second step in this learning process is that you want to get E in of G approximately equal to 0. Okay, now there's no high probability there. That we can verify, by just running G on our data set and computing E in of G. Okay, so no problem there. Okay. Now, there's something else that we have to give up. Okay, when we look at this 2-step process. Okay, because here are the conditions in order to accomplish the first step. So here are the conditions. Okay, so conditions. So conditions. 1. And most of these conditions are coming from the need to accomplish the theoretical step in learning, this theoretical first step. 1, you've got to fix the hypothesis set ahead of time. So you have to fix H and guarantee me that G will come from H. Okay, so that's not such a big deal. You can pick it whatever you want, but now we know that there's a trade-off in picking this h, and now it's a real challenge to figure out what's the right h to fix it to. Condition number 2. Okay. Condition number 2 is that your data, in order to establish this set, for whatever data set, we can always go and compute this. But in order to establish this set, it must be the case that your data was generated from this random process that generates data, which we call the probability distribution, and it has to be generated IID, independently, identically distributed according to P of X. So the data is IID according P of X. Okay, not a huge deal. Right? I mean, this is the case in all applications that, your data comes from some random process. We're calling this P of X. But the important third step, important third condition is, it must be the case that we are talking about the Eout that is relevant to that same random process P of X that's generating data and the same target function that's generating the data. So Eout is for a random test point, according to P of X, the same P of X. Okay, the same P of X. Now, this relates to a requirement in the bin/sampling model that when you pick a sample from a bin, and you look at its in-sample fraction of red, that tells you something about the population mu, the population fraction of red, for that same bin that you took the sample. Okay, and if you mess around with anything here, basically you're trying to make a conclusion that Eout for a different bin is close to E in, that you have gotten from some other bin. And that's why I said that there are very subtle ways in which this principle gets violated. And that is equivalent to violating that obvious principle with the bin model, with the sampling scenario, where if you take a sample and look at the fraction of red, that tells you about the fraction of red in that same bin. Okay? And usually when something has gone berserk and haywire, the problem is here, okay, but for professionals. Okay? And for amateurs, the problem is usually here. Okay, so this fact that we had to fix h ahead of time leads to another interesting thing that can happen, which is, okay, so let's see what happens. You fix h, okay, and you do everything as required. So you generate the data according to P of X, and, you're going to generate the test point according to P of X. Okay, so you've generated the data, you learn, you search your hypothesis set, which is now fixed, you pick your G, okay, and since the hypothesis set has to be fixed, remember, you cannot change it. Okay? So you've established that for the G that you've picked, whatever E in you get is going to be approximately equal to the E out you get. So you can reach outside. So you've established this. Okay. But now there still is a price for establishing this theoretically, is that now you go and look at what was actually E in. Okay. And if E in is 0.055%, oh, you jump up and down for joy. You succeeded. You got E in close to 5%. Okay, and E out is close to E in, so you've got a 95% accurate classifier out of sample with high probability. Okay. But what do you do if E in is 0.4? So your in-sample error is 40%, and that means your out-of-sample error is approximately 40%, so you only have a 60% accurate classifier out of sample, and you're going to be assigning credit according to this almost random classifier? Well, did you really find the best G in your hypothesis set? Yes. But, too bad. Your hypothesis set was, limited because you fixed it ahead of time, and I picked the best G, and it just happens to be bad. What can you do? Done. Done. You're done. Okay. So, basically what you do is you say, go back to your client and say, listen, man, you have one hell of a hard problem. I tried my best. I ensured the first step. I tried my best. I fixed the hypothesis set. I picked it and this and that. Okay. And, I got an in-sample error of 40%. So that means that out of sample, you expect this thing to be 60% accurate. Okay. And, if that's good enough for you, then here you go. But otherwise, you know what? I failed. So this is the other thing that comes out of the is learning feasible question, which is that it is only possible to learn when you simultaneously accept that it is possible to fail. So it is possible to fail. And in fact, it must be possible to fail if you are to be able to learn. Because if your hypothesis set is too large, in which case it's not possible to fail. You will always get E in close to 0. You cannot get E out approximately equal to E in. You will lose control of the first step of learning. So it has to be possible to fail. And you should think about this and say, it's natural, okay, that it should be possible to fail. Because, if you're not willing to fail, you can't learn. You have to be willing to, otherwise you'll be just learning trivial things. If you want to go after complex, hard problems like complex target functions, then you go after them. And there has to be a situation where, it's too complex for you to learn. And that's certainly the case for humans. And why shouldn't it be the case for machine learners? Okay. And so essentially what the hypothesis set does is it specifies a stopping condition. It says that, once you've exhausted the resources in my hypothesis set, perhaps by searching the hypotheses one by one, once you've exhausted those resources, what I can guarantee you is that as long as you don't deviate from the boundaries, from the confines of this hypothesis set, I can guarantee you step 1 of learning. And if you failed, you failed. You're done. Okay. And we will discuss, if we have time, or we will maybe in one of the next lectures, what happens, what's going on with these people who say, oh, look, I failed. And then I try, and only then do I try another hypothesis set. But if I didn't fail, I would have stayed with this hypothesis set. That introduces complications. Okay. That introduces complications. You're not allowed to do that. Just not allowed. Okay. Okay. Now, so what are the prices we had to pay in order to make learning feasible according to this 2-step process? So, you fix the hypothesis set and that introduced the possibility of failure. Okay, the data has to be generated according to probability distribution and the target test point has to also come from that same distribution, the same bin. You're testing yourself on the same bin that generated the data. Okay, but what did we gain? Well, we gained the ability to learn according to this 2-step process and look at the generality. Our learning approach is general. So 1, it applies to any machine learning problem, any learning problem, any target function, any target function. It applies to any random process that's generating the data. Any P of X. Okay. It applies to any hypothesis set as long as it's fixed ahead of time. Okay. I don't care. Is it perceptron? As long as it's finite, but I don't care. Is it perceptron, neural network, like, or whatever. So any hypothesis set. And one more any. Okay. Any learning algorithm A. Any learning algorithm A. So in other words, I don't even care how you pick your final G from H. This entire is learning feasible theory applies. Any. So you could choose to pick the best looking hypothesis, a mediocre looking hypothesis, the worst looking, whatever. The only thing I need to guarantee this theory working is that you obey these conditions, and this condition in particular, which ensures that G came from H, but I don't care how you got it from H. You could have picked randomly, you could have picked this guy, you could have picked, hypothesis 1, you could have picked randomly, you could have picked the best looking one, best looking with the whatever you want. I don't care. Any. General. And that's very good because the target function is truly unknown and we would like to address hard problems. Okay? And a multiverse of problems. Okay. So, let us speed erase and then we'll come back and discuss some issues that might be nagging you and also get closer to practice. But that's the theory. That's the is learning feasible.